Hello. I'm John Pavan. I'm a team lead at Bloomberg.
And I'm Heather Crawford. I am part of a team that trains all of our newly hired software engineers in the internal Bloomberg tech stack.
And today we're here to talk to you about why software engineers are so hard to replace. That was our original title slide. Okay. This talk is effectively in two parts. This talk is effectively in two parts. The first part is going to be about kind of the history of all the things that were intended to replace software engineers, why it didn't replace us, obviously we're still here, and what we have gotten out of those attempts as an industry. The second part is going to be about the fundamental reasons why we're effectively irreplaceable, and Heather will be we'll be covering that part. So the origin of this talk was that we had an internal conference, and Heather and I basically both proposed exactly the same talk, and so we decided to team up rather than to compete. Somewhat collaborative. At a personal level, the reason that this is somewhat important to me is because early on I was not intending to be a software engineer, but I did like computers and I did like programming. But for reasons that I'll go into in a minute, I thought that software engineering was just going to be something that everyone had to be able to do in the future, and that you needed to have some other skill set in order to actually have a career. Obviously, I now know that I'm wrong. But I think one of the big reasons why I thought that was through most of my youth, there was, and continuing since then, there was always someone talking about, oh, this new technology is going to make software engineers obsolete, or this new technology is going to make software engineers much cheaper. It's going to make them much easier to find. So that's a lot of what this history is about. Before we actually get into the history, there's a couple details. One of them is that I have a lot of timelines on the history slides. These are intended to give you information about when things were happening and provide a frame. These are not intended to be complete. So for example, this one is about third-generation programming languages, and it's clearly missing a few, most notably JavaScript. In previous presentations of this talk, we've discovered that not everyone knows what I mean when I say programming language generations. And these are not about the chronological order in which programming languages were created. This is much more about capabilities. So for example, bytecodes, the various bytecodes are the first generation programming language. Assemblies are the second generation of programming languages. And the third generation of programming languages are those that you think of as general purpose. So these are your Fortran, your Cobol, your C, your C++, your JavaScript, your Python. Fourth generation are highly specialized. We'll talk about them in detail later. We'll also talk about fifth generation programming languages later. And the sixth generation of programming languages are probably the ones from that took place in the foreground of Dune. Okay. So when you think about things that were intended to replace software engineers, the earliest thing that I was able to find was the thing that all of us struggle the most with, which is programming languages. In particular, Fortran and Cobol were very explicitly intended to make it so that physicists and mathematicians and business people wouldn't need to work with software engineers to translate their algorithms and their formulas from paper into assembly in order to run on various mainframe computers. And these were largely successful. They allowed a lot of physicists and mathematicians and some business people even to implement their own logic. I know a lot of people from physics that wrote a whole bunch of code about 1980 and basically have used that for their calculations for the rest of their career. Now, obviously this didn't completely eliminate software engineers. In fact, I would say the existence of the higher level programming languages has actually been fairly beneficial to us. But it did free us from kind of the monotony of having to do that translation logic. or having to translate logic from paper into assembly for people. And allowed us to work on things that were much more complex, much higher business value, much higher levels of abstraction, and effectively allowed us to have the industry that we have today and celebrate. The next couple of items need to be framed in terms of something called the software crisis. This is something that I want to say came out of NATO, but it might have been the UN. And depending on exactly who you talk to, it's the software engineers aren't good enough, software engineers are too hard to train, we can't find enough good software engineers, things along those lines. So this is from the mid-60s, and it ended in the mid-80s with a paper called No Silver Bullets, which was basically a paper explaining that we were not able to find magical things that would suddenly make everyone super productive, with kind of the specific definition being an idea or a technology that would allow people to be 10 times as efficient or 10 times more productive inside of a decade. Now, of course, I personally think that there are situationally at least some silver bullets, which I'll also mention. So during the software crisis, people introduced new paradigms. So a big one was object orientation. If we talk about the history of it, probably the earliest thing is the MIT Sketchpad from the 1960s. It wasn't a programming language, but the UI was written in an object-oriented way. And then we get Simula, which was done by a company that was managing shipyards, and so objects and our boats and cranes and containers. And then we get the first general purpose one with Smalltalk. And then additional later languages, so Modula 2 and object-oriented Lisp and Oberon, added a bunch of things like being able to check types across modules. So it matured fairly quickly. And at least I remember when I was first learning software engineering that everyone talked about object orientation being really the only way that you could do it. And many of the languages that came out or that existed before it and the ones that came out after it basically all feature object orientation in some way. It was either added or it was an original design decision. Of course, we now know that it's not universally the best solution, but for many applications, it does indeed actually work very well, particularly if you're talking about a UI or something that's event-driven. These are things that humans can think about in terms of individual objects, and therefore that match between how we think and how the computer is being programmed works out quite well. So we get new techniques. There was also an attempt to take the advances that were being made in other areas of engineering with computer-assisted design and apply those to software engineering. And these are the computer-assisted or computer-aided software engineering, or CASE tools. And these are things that actually were quite popular kind of during the 80s and until about 1990. And we actually got quite a lot of stuff out of this. So UML probably came out of the CASE tools. A lot of the tools that you use to kind of do your initial diagrams or to try to create charts and things to explain your logic to people during presentations, or to share with your coworkers, hey, I have this cool new idea, I've quickly sketched it out, came from these things. But or if when you were learning programming and you were of a particular age and you learned via a visual programming thing like Visual Basic. So like there are use cases for it. But it suffered from a bunch of problems. A big one of them was that there are a large number of these and it took a great deal of training to actually be able to use them. So it was slow to spin people up, and also the inputs for one didn't necessarily, if you put the same inputs into two of them, you didn't necessarily get the same thing out. So that's a big problem for enterprise adoption, because if you only have one vendor, then they take all the money. And you also had other problems like the output of them, because it was usually not going into some engine or something like that knew how to interpret them, knew how to interpret the inputs. It was usually producing code. That code was usually not especially good, and it was not especially flexible. So if you were developing a website with some tool that was designed to make websites, although I think 1990 is a bit early for websites, they would produce functional code that worked and did what it was supposed to. But if you needed to do something that was beyond what the tool supported, you had to rewrite an enormous fraction of it because it just did not offer that sort of flexibility. This is something that we'll revisit a bit later. We also got new methodologies. I don't think I need to talk about Agile, although I can share a personal anecdote. So when I was an infant, my parents lived next door to Hiro and Hiro Takeuchi, who's one of the original on the original paper, and they traded babysitting duty. So they fed me lots of seaweed to make my hair black and shiny. Clearly worked well. But I would actually like to talk a little bit about waterfall. So waterfall is something that maybe a few people in here have used, but a few people raised their hands. But it really was an attempt to increase certainty, and it's like the first attempt at software development lifecycle. And it kind of came from a military again, so probably NATO, where they wanted to make it more predictable on how things would actually how software projects would actually get produced. And so if you haven't used it, you have one type of design, you have another type of design, you have a third type of design, maybe a few more. Then you have an implementation phase, then you have one type of testing, another type of testing, another type of testing, a couple of release phases, and finally it goes out into the real world. And it was supposed to reduce uncertainty because all those design phases would allow you to onboard people using the literature that was produced there. Everything would be thoroughly vetted at every stage before you advance. So you would fully do your design, then you would fully do your implementation, then you would fully do your testing. The problem with it was that if you found a problem, you usually couldn't solve it in the phase that you were in. You usually had to go back a couple phases and then start the process advancing again. So it didn't actually turn out to be any more reliable to produce software that way. But we did get software development life cycles out of it, so there was a benefit. We also got new programming languages, so Ada in particular from about 1980. And Ada was an attempt to fulfill the Steelman design documents or something like that. Also the military. For some reason they keep showing up in this. Basically there were no existent languages that fulfilled these requirements. And they included things like memory safety, probably last year's hot topic. And there was an enormous amount of enthusiasm around Ada as it was being released, with the authors of Ada going so far as to predict that in the future there would only be two languages, Lisp and Ada. And that didn't quite work out. The big reason why was that Ada was actually a fairly complex and difficult language to work with. And it had slow compilers, and its runtime was quite slow as well. So people had better options. But it has effectively survived, and it does get used in things where there's kind of some sort of safety requirement. But if you think that we are threatened by Rust, Rust does everything that Ada was supposed to do better than Ada does. So the Ada community, I think, is much more concerned about it. So I'd now like to move out of the software crisis and talk about JavaScript, because JavaScript is a language that twice during its development was advertised as something that was going to make software development much cheaper or make it much easier to find software engineers, which is kind of the same thing. So at its inception, I want to say mid-90s, it was created at Netscape, and it was basically intended to provide an easier way to develop websites than the cascading style sheets in HTML and raw HTML. And it had a specific goal of trying to make it so that you could have dynamic websites, which wasn't actually possible at the time, but JavaScript did make it easier to develop websites. In 1999, Microsoft decided that it was going to try and use its web browser as kind of the fundamental technology in order to build other programs. And created Internet Explorer 5. And Internet Explorer 5 allowed dynamic web pages because they were using it as the engine for Outlook, and they wanted to be able to refresh your emails in the background. So then over the next couple of years, every other web browser has to add the same capabilities. And everyone, of course, does it in a slightly different way. So late-ish 2000s, you get jQuery, which provides an abstraction layer. So you can program in jQuery, and then you don't have to worry about all the different dialects of JavaScript. And all your web pages start to look and act the same. And 2009, we get the other event where people talk about this making some sort of software development cheaper and easier. The first of them is ECMAScript, which adds a bunch of things, including MapReduce. And the second is Node.js, which is basically allowing JavaScript to run outside of the web browser. So you can use it for backend development. And the buzz at the time was, now anyone that can make a web page can also make the server-side software. Therefore, it's going to make everyone cheaper. And I personally think this is insulting to people that develop web pages, because just someone that has a different skill set than me does not make that an inferior skill set. But people have gone and used Node.js and JavaScript to develop very sophisticated and very valuable pieces of software that run on the server side. Not to mention all the stuff that people do around prototyping using it as well. And of course, the latest iteration is TypeScript, which is kind of I think the most modern version of JavaScript that's in use. Okay. So I also do think that there actually are some silver bullets. And again, these are things that make people dramatically more productive in a relatively short period of time, with kind of the threshold being over a decade, making people an order of magnitude more productive. The first of these are well-tested libraries and software frameworks. So if there's a library that exists that is well understood and it does the thing you need it to do, rather than write it yourself, just use that library. You don't have to re-implement JSON or JSON parsing, to go back to an earlier talk in this conference. Software frameworks are a little bit different from well-tested libraries in that they are the program themselves, and they provide nice hooks for you to be able to add your business logic or whatever specific thing that you need the program to do. I think the ones here are all UI-based, but there are also software frameworks for things that run on servers. So Mac app is probably the first one, mid-'80s. Then in the '90s, you get Qt and GTK. In the mid-2000s, you get Django, which is a Python-based framework, and it's intended for things that are driven by databases. And then once you have ECMAScript, you start getting a bunch of Chromium-based frameworks, Electron being an example of those. And so these are really quite handy. They really do speed up software development because you don't have to worry about how you're going to maintain connections or how you're going to connect to other, how the client software is going to connect to your service, or how to create the window for the screen and things like that. All of these software frameworks can do that for you. Another thing that I think is a silver bullet are fourth generation languages. And these are very, very situationally silver bullets. So these were created to save on punch card usage. So specifically, Mark IV was intended to basically take you down from like 30 to 60 punch cards worth of Fortran to, at least in the situations where Mark IV was useful, you got like one punch card worth of Mark IV. Of course, that one punch card worth of Mark IV is like one statement in SQL. And so, these are incredibly, we don't use punch cards anymore, obviously. Or maybe you do, I'm not judging. But if you are in a situation where one of these applies, so this particular group is probably most familiar with Shell and SQL. If you're in a situation where one of these programming languages applies, it really is much faster to do stuff, or thank you, and to use them. And there is a special case of SQL, and that is that spreadsheets. So most people don't think of spreadsheets that are something that competed with software engineering, but they have actually done a good job of freeing us from a particular type of monotony. And that is that it used to be that if business people wanted to test out different theories to see how different business decisions would impact the bottom line, they would have these huge pieces of paper and a bunch of people making calculations. And computers replaced that, letting those people do something more productive. Then you had the programmers that would have to work with the business people in order to actually program those choices and then make the calculations to see what the result was. And spreadsheets, starting with LandPAR and mainframes, and then VisiCalc, which drove early Apple adoption, and Lotus 1-2-3, and Microsoft Excel or Google Sheets, whichever one you happen to be using now, really made it so that the business people can do this themselves. And a lot of people that are using spreadsheets on a regular basis are actually really good at them, and are programming in them and doing interesting things. I'm not one of those people, so don't ask me for an example, but there are some really impressive spreadsheet people out there. And now I'd like to turn to something a little bit sad, and that is 5th-generation programming languages. And I'm not talking about OpenAI. So there were a bunch of projects in the 80s and 90s that were attempting to figure out how people would use computers in the future. The most interesting of these that I found is the 5th-generation computing system from Japan, which ran from the 80s, like 82 to 94 or something like that. And it looked at how hardware would evolve in the future and how software could evolve in the future. And in particular, it tried to figure out how you would create the next generation of programming languages, and this in the way that I'm using generations. And that you would have kind of a series of logical statements, which would be your data. So your data would be, when this happens, this other thing is true. When this happens, this other thing is true. And then your program would be a set of logical axioms. And then if you wanted your program to run, you don't even have to compile it. All you have to do is say, okay, computing system, see how this data and these axioms do their inference thing, and then it would spit out results. And it turns out that this doesn't actually lead to good results, although there were interesting attempts. There was an attempt to make a programming language for managing databases. There was an attempt to make a programming language for doing legal reasoning. And it turns out that the fundamental flaw is that figuring out an efficient way to do something is itself a hard problem. And that requires humans for anything that's vaguely complex, because of something that Heather will talk about during her portion of the talk. And that brings us to modern AI, which compared to what was being done in the 80s and 90s is actually, in my opinion, wildly unambitious. It seems to aim for, we are going to reduce how much time people spend coding. It's going to be a coding assistant. And since we're still in this, we do not know what tools we're actually going to get out of this or how useful it will actually become. So I'd now like to hand off to Heather, who will talk about the principles and our characteristics that...
I'm supposed to say, make us irreplaceable. So thank you, John. I'm happy to say that I was actually around for a lot of that history. What about you out there? Put your hand up if things resonated for you. Yeah, if not, cool. Next time. Okay, so John set me up for this. We might have practiced. I don't want to say that we're hard to replace. I want to say that we're irreplaceable. Okay? Not that it'll happen if, AI just gets better or these no-code options just got better. We're irreplaceable. Now, before I tell you why, we have to really look at what a software engineer does on a day-to-day basis. As I told you when I introduced myself, I teach newly hired software engineers about the Bloomberg internal tech stack. And they're by and large new college grads in their first jobs, sometimes their first job ever. Like they never even flipped burgers. And they think that we all sit around all day for 8 hours a day writing code. Who does that? Put your hand up if you do that. No. So let's look at what we did. So the results that you see here in this beautiful pie chart, okay, are from a study of 5,000 software engineers from Microsoft across all experience levels and across a multitude of teams. Now, you could say, cool, Heather, I see the bias. Okay, Microsoft, okay, yeah. But if you look hard enough on the internet, you will find this replicated a lot of different places. But what we find here is that a little less than half, only 48% of the time are we doing what we call development. Now, I'm going to talk in a second, I'm going to break down that blue part of the pie chart there, the 48% for you. 36% is doing collaboration. Talking to people about problems, talking to people about design, thinking about how we can do things better. We're going to come back to that over and over again. And 16% is doing other important things like having non-work-related conversations. Why is this important? Because sometimes that's exactly what we need to solve the problem that we're thinking about. But it also, that 16% also involves things like, I don't know, having lunch, using the restroom. All of these things were included in that part. So a little more than half of the time, we're not actually doing what people think software engineers do. So let's look at the part that people do think we're doing. And what we'll find is that about a third, 31.3%, is actual hands-on keyboard coding. Now, arguably, I would consider the red part, the one that says 29.2, bug fixing, that's also hands-on keyboard writing code, because guess what? I don't know about you. I have never written bug-free code, ever. Okay, so now we've got about, I don't know, 2/3 of that 48% is actually hands-on keyboard writing code. So what's the rest? Well, writing documentation. You do write documentation, right? Of course you do. Reviewing code, not only reviewing other people's code, but parsing through and understanding the reviews that we get from other people. It's writing specifications about what the code should do. Hopefully that came first. I don't know. Okay, and also testing our code. I'm not gonna lie, testing is not my favorite part of writing software, but I see its value. And it's a little bit sad that we only spend 16.7, or at least those 5,000 Microsoft engineers spend 16.7% of the time. Either they're really good at it and they just know how to write really good tests, which I would believe, okay? Or maybe we don't do quite enough of it. But what we've learned now is that the job of a software engineer isn't really actually writing code. It's a whole bunch of other stuff. All of you know this. This is your day job. I include myself in here. But other people don't. So what do we bring to the table? So all of the things that John explained to us, that amazing history lesson, including modern AI, is transformative in some way. And what does this mean for us? This means that we have to evolve. It means that these transformations that happen bring us tools as developers that we can then work into our workflow. And these tools benefit society, maybe not directly. Okay, so guess what? I bet you a rando person on the street was not going, hey, you know what? I'm going to write COBOL. But they are saying, I'm going to use AI, right? So sometimes it's direct and sometimes it's indirect. But no matter what, the tools that we create with the technology allows us to transform the world in lots of really cool ways. So whether that's direct or indirect, that technology has benefit. Now, let me give you a couple of examples. The first are, I want to pick on COBOL, which allowed business people to write code, and Fortran, which allowed scientists to write code. And because of this, we were democratizing the idea of writing code, the act of writing code. It no longer had to be somebody with a whole bunch of formal training, although we learned this morning in the keynote that a lot of us don't have that. We just pressed keys on a keyboard until it clicked, right? So the other example I want to give you is the computer. And now I have to try to get my third hand out here so I can juggle these. The computers that transformed us. Okay, so it used to be that a computer was a big thing in a room somewhere, and some highly trained tech had to go to that room and do stuff in order to compute. But now we all do it, apparently before we poop. That's what we found out in the keynote this morning. I didn't make that up. And so computers have become mainstream, and we don't think twice about using a computer, where it wasn't that many years ago that was hard and specialized. So technology is transformative, but the cost of this transformation is disruption. And this disruption is inevitable. All of the historical tech that John presented to us has been transformative, has been disruptive in some way. In terms of what it provided to developers for tools, to society in general, that disruption is nothing new to any of us in the room. We go, oh, okay, cool, there's a new framework. I wonder if that framework is going to help me. And you decide as a developer, yes, it will, or no, it won't. Or maybe you decide, yes, but not right now. So strong developers are going to be able to predict what doors are going to open because of a new technology, while other doors close. Now, sometimes those doors closing is awesome. Like, you know what? I don't want to have to write code to connect to a database ever again in life. Throw that in a library. Let me call it. In fact, don't even do that. Just let me connect to my database. So what we need to do in order to remain relevant in the face of this disruption is to evolve. And this evolution is necessary. You can see it over time. I have never written an API in my life because I don't have to. Other people have done it before me because of the tools that they had in their toolkit. And what this means for all of the rest of us is that experienced developers aren't worried. We've evolved before, and we will evolve again. And so we don't have to be scared of these transformations that change us. The people who are scared right now in the face of AI are the ones who don't have the deep skill set that they need in order to evolve and in order to change. So what do we need to have in order to evolve? We need to understand that complexity is what we do. Being a software engineer means being comfortable with complexity, means saying, wow, that's really hard, and doing it anyway, of not knowing how to do something and being like, cool, that's Tuesday. Tuesday being just happens every day. I want to read to you two quotes. Okay, they are from Ernest Shackleton, who had a failed attempt to travel to Antarctica. So the first one is, difficulties are just things to overcome after all. And that's really what our job is about. I once read a book, and I wish I could remember the name, but the book was about a C programmer who had a bug. It was fiction, but not really, who had a bug that he could not solve. And his job gave him time to try to solve it. And I'm going to ruin the end of the book for you. He never solved the bug. Actually, yes, he did. But in the time of trying to solve that bug, he actually went literally crazy. He could not figure out what was wrong. In the end, I think it was an off by one error. Like, it was something, pretty obvious. But by this point, he had driven himself crazy. Okay, so difficulties, as Shackleton says, are just things to overcome. So all we're going to do is, when we see a new tool and we deal with complexity, we're going to go around it, over it, through it, under it, whatever we need to do in order to bring that in, because that's our job. Now, the second quote I want to read to you, I will apologize in advance. It's gendered. Okay, I apologize because I really hate gendered quotes, but it came from a while ago, kind of a long while ago. So the quote is, "Men wanted for hazardous journey small wages, bitter cold, long months of complete darkness, constant danger, safe return doubtful, honor and recognition in case of success. This was the advertisement Shackleton placed in a newspaper to try to get people to come along on his journey. And he was flooded with people who wanted to come along. Are you serious right now? You're saying, I'm not going to get paid much. I'm probably going to die. It's going to be really uncomfortable while I'm doing it. And all I really get in the end, other than this pay, is bragging rights. And yet people flock to it because it was new. It was hard. It had never been done before. And it probably wasn't going to succeed. And that is what we do. I kind of think code maintenance is a little bit like that, right? When we have to maintain code, it's a lot of like when to upgrade. You know, when you say, look, your job is going to be to look at other people's code a whole bunch and make sure it doesn't break. Why would I do this job? And yet we do, right? And why? Because it's hard. It's complex. Why are we able to do this? We're able to do it because we can think abstractly. We can say, hey, that solution to that problem worked for that one. This other one worked for some other problem. What if I put them together? Would it work? I don't know. Let's try it. Let's hack out some code. Okay, so that abstract thinking allows us to take new approaches to problems that we don't know how to solve yet. Remember the complexity on the previous slide? And in all of the historical examples that we've seen so far from John, the key differentiator between those who succeeded and those that failed was being able to think abstractly on how that tool was going to change them, change their job, change what they produce. And so this means that we have to think of our current job in terms of what it's going to become and how that tool is going to either help or hinder as opposed to just jumping on the bandwagon. And AI is a perfect example of this. Okay, who has had a bad experience with AI? Who's had a good experience with AI? Yeah, almost the same set of people. And that's for a bunch of reasons. The first one being it's still kind of new, it's still kind of dumb. Even the reasoning models that are out there. Has anybody worked with an AI agent before? Oh, they're frightening. They like do stuff and open files and put code in other files and call APIs, and you're just like, I've lost control. Okay, so abstract thinking is one of the benefits that we bring. And using things like the historical examples that John gave us, as well as AI, allow us to think at a higher level of abstraction. And what I'm going to call that through the rest of this presentation is the brain surgery code, or the brain surgery problem. Any brain surgeons here? Excellent. You're going to help us. You know what? That had to happen. Not for free. Okay. So what do we need to do in order to use this abstract thinking? We need to rely on the fact that we're really good at advanced problem solving, that we don't know how to solve all of these things. Exploring and questioning approaches, right? Yesterday, I know Cal was talking about how he throws ideas at the wall and like maybe 1 in 6 might stick, but it doesn't stop him from throwing those at the wall. And we're going to come back to this as well, is that we get to use our advanced problem solving to be able to say, is this the best approach? Especially in the face of multiple competing preferences or multiple competing goals of what we're trying to do. So it allows us to do things like systems design and architecting new systems that haven't existed before. Because guess what, everybody? You can quote me on this. AI is just code. Somebody took the tools that other people created and created a new one for us. So human developers really shine in taking our deep experience and efforts in learning our craft to problem solve better and to problem solve things that we hadn't thought of before. And this makes us adaptable. And this adaptability is what makes you irreplaceable, makes you the person who is going to be able to step up and use this new tool. So where could this be helpful? One of the things that John lightly mentioned was what we call a no-code tool, right? Does anybody remember the WYSIWYG editors where you could drag and drop and it would create a web page for you? Optional dancing hamsters on it, if anybody remembers that part of internet history. Okay, yeah, I can still hear that music in my head. Okay, so these WYSIWYG editors, what you see is what you get. It created crappy code. Anybody ever look at that code? I'm not even an HTML developer. It sucked. But the thing it created, the web page, looked okay, loaded most of the time, probably did what it was supposed to do until it didn't anymore. And so you needed somebody who knew what they were doing to come in and fix it for you, or else you would amass technical debt. You would amass a lot of unmaintainable code. And so it wasn't about the visual nature of that code. And a lot of what our jobs became is somebody basically vibe coding. I hate that term. Basically vibe coding with their WYSIWYG editor and then going, not my circus, not my monkeys anymore. And we had to swoop in and use our adaptability to fix it. So the job changed. Now, do I want to maintain somebody's janky web page? No, not really. Okay, and now we kind of don't use them anymore. I hope. I don't know. I guess we kind of do. Yeah. That's sad. So, optimization becomes something that we have to care about and think about deeply. Now, when I say optimization, I don't mean big O, okay? I don't care if AI can write something that is like O of log n and mine is stuck at O of n squared. Don't care, okay? I'm not talking about optimization. I'm also not talking about memory versus CPU time optimization. What I am talking about is finding the balance between writing maintainable, readable, understandable code, okay, and something that isn't slow or memory bound. Okay, so I didn't even say like efficient or fast. I said not slow, not memory bound. Okay, do not do premature optimization. And it's really humans that know how to do that, who know how to meet that balance, right? It's not the AI, and it's not, Fortran. As if John created Fortran. So the upshot of this is knowing what to get exactly right and what you can kind of let slide is something humans do. Okay, the AI will lie to you about what is important. Okay, so all of this up to this point has led up to the idea of innovation. Who recognizes what's on the screen? It's a Google Glass. Who used one? Me and one other person. It's because we're both researchers, right? Google Glass was a wearable computer, okay, that we wore like glasses, and you've never heard of it and you've never used it because it's gone. So put your hand up. This is hard to do with people now, but put your hand up if you think that means it failed. Like, is it gone because it failed? I think it succeeded. I think it succeeded wildly if you think of what this innovation was supposed to do. Who has a smartwatch on right now? Who has one of those like ring things that you put on? Google Glass opened the door for wearable computers that we see all over the place now. Even this smartphone in my pocket is kind of a form of wearable computer. This thing was an abomination, okay? It was hard to look at that little screen. That big chunk in the back there was the processor. It burned my head, okay? But it was a form of innovation. And here's the thing with innovation, is that sometimes, most times, in fact, it's going to fail dramatically. But we can reframe that failure into something that actually shows a great leap forward. And humans are good at that. Okay, so where are we at now? Everything that I've been talking about, all of the concepts, all of the attributes that we as human developers bring to the stage come down to this. We are irreplaceable as long as we make sure to evolve with the times. Why? Writing code is the easy part. And that's what all of the technology that John gave us, including AI, is good at. I predict it will never be good at the parts that we are. Therefore, we're irreplaceable. Now, here is the scary, scary, scary part. You can't write the hard stuff without first learning the easy stuff, okay? You cannot jump over the experience of becoming a truly experienced developer. You vibe coders out there, none of you, okay, are never going to take away my job, because the depth of experience that we all bring to the table is really where we gain. So up to this point, I would trust you and believe you if you said, Heather, this is all just your opinion. You put a bunch of words on a slide and you told me a story and here we are. I'm not picking up what you're putting down. But you know what? A whole bunch of people on the internet, look it up, agreed with me. And that means it's true, right? Of course. So I want to get theoretical on you. In computer science theory, the program synthesis problem is being able to find a program out of all the possible programs written in a given language. Let's pick C++, okay? And finding the one program that is going to solve a particular problem. Now, all of these no-code tools, WYSIWYG editors, even AI, are really just trying to solve the program synthesis problem. They are trying to find that one program that's going to meet your needs, okay? Maybe in whole and in part, but here's the problem with this. The harder the problem, the more complex it becomes, the less likely you are to find that one program, or even a partial program. And it probably will be ugly and janky like WYSIWYG editors or anything that comes out of an AI, and you're going to have to fix it. So your job is safe, even if you go back to computer science theory. Now here's the thing. Does P equal NP? This is an unsolved problem in the realm of computer science. We don't know whether the set of problems that exist in P are the same as the problems that exist in NP. Maybe you believe the opposite. Maybe you believe it's not true. But what the innovation that we've been seeing overall allows us to do is start thinking about intractable problems and finding solutions for them. And so don't see these tools as something that's going to hold you back, but something that's going to accelerate you. Okay, so I will leave you with this. My advice for the future. Okay, everything that we have in front of us is going to be harder than the stuff that came before. Now, that's partially because we already know how to solve it, okay? But also because we're freed up with these new tools. But don't panic. Your job is safe as long as you continue to evolve and you continue to grow. But learn your craft. This is not wasted time. You are going to be able to innovate and be better and do better things if you learn your craft. And I don't mean like, oh, well, I had to do it that way. Okay, oops, I went backwards. But we have to embrace the new technology that's coming. You don't have to take everything. I never learned Cobol. And we have to teach the next generation, because one of the things I did not mention in this talk is that AI learns on what came before it. And if nobody learns their craft and nobody gets better, then all we're going to do is repeat the same crap that AI is generating now over and over again. So it's up to us to teach the next generation so that we don't end up with AI slop everywhere. Okay. Thank you very much, everybody. Very happy to have talked to you today. And John and I are both here for your questions. So who has questions for us? All the hard ones are John's.
Or if you just want to share a story.
As you're teaching people, because you're in our training staff, what do you tell them to use AI for? What do you tell them it's good for?
One of my very favorite things to ask them to do is if they've created a solution to a lab or a problem that we've given them, I tell them to put that into the context of the AI and have it interview them to test their understanding of their own code. This is game-changing. So I did this with a solution to one of our my solution to one of our labs. And the very first thing it pointed out, it said, oh, you've reused, this was in Python, sorry, not sorry. You've reused this variable on this line and this line. What are the pros and cons of having reused this variable? I was like, oh, I reused a variable? Ooh, that's bad. And I had this interesting conversation with the AI, but it has this way of like honing in on the junk in your code and saying why. Okay, so that's one of my favorite ways to get them to use it. But we also try to teach them to have a healthy disrespect for what it creates and not just take it as is. So thank you for that question.
Yes, interesting thing I wanted to say, which is something I heard somewhere on YouTube, is one person said, well, if AI allows you for people to code 2-3 times faster, 10 times faster, you don't fire people, you hire more people because they will create more products.
Absolutely true. AI slop is real.
Yeah, all this talk about having new frameworks and then new technology and new tools to make us basically at the end more productive, or at least maybe hoping to reduce the time to market and the cost to develop in exchange to burning insane amount of compute and RAM. At some point, should we draw a line? Because you can argue that, yeah, C++ is completely more expensive than if you handcraft all the assembly yourself, assuming you can put it all in your brain. I don't think you can anymore. So I think C++ could still be at the cutoff of yeah, this is literally almost a straight positive. Then you start to go on Electron and look at how much RAM and CPU Spotify will use. And then you go into AI and how much GPU compute you use to make a hello world in a language you don't know about. At some point, maybe it's the premise because it's not software developers who are the one deciding what is it as unsustainable to go that route. But I think this is a question as a professional we should be asking ourselves.
I agree. I think one of the things that's important to remember about kind of the modern AI push is that we really don't know what tools we're actually going to get out of it. And we don't really know how it's going to end at this point. And I think that giving this talk 6 months ago, which we actually did, the questions around AI were actually quite a bit more concerning because I think it felt like there was kind of more of a steady set of advances where it really does feel like it has stalled out a fair amount in the past 6 months. Yeah, there's big questions around efficiency, but also remember that a lot of the more modern code or the more modern applications are actually doing quite a lot more than the stuff that ran on the 460K is all anyone will ever need computers. And in many cases, those changes are not necessarily in terms of the changes to the algorithms and what they're actually calculating. A lot of times that has to do with accessibility and usability. So the idea that we're all carrying around a phone in our pocket, and everyone from a 2-year-old to people that are very, very senior and did not grow up with computers and maybe are suffering some from physical ailments, can use those is actually quite significant and really has increased the level of availability of tech and improved many lives.
And I'll just add to that, I think it was Sam Altman from OpenAI who said, would you all please stop thanking the AI because that's burning more cycles and more electricity. And I am really tempted to just like put a whole bunch of please and thank you at the top of it so that it has to keep processing. Yeah, good point. What else do you want to ask us?
Thank you. Thank you, great talk. I just thinking about that we're like moving to some gap, right? So we are irreplaceable, but in some point we will not have anyone to replace by. So like Stack Overflow. So it taught the AI when we had a lot of questions there. Now AI works instead of the Stack Overflow. So we have like decreasing amount of questions. At some point, we will not have enough data on Stack Overflow to teach new AI. What we will do? So how to solve it? So, for example, like my wife. So she returned from maternity leave. Applied there, applied here, refused. And she said, oh, I just go to sales. I don't want to bother because there's AI. I don't have power to compete with these prejudgments. And just already she sends resumes to different companies because there is no future.
So she has a hard job for sure. She has a lot more learning to do than, if she had been in this position 10 years ago, but I predict she can do it. When it comes to Stack Overflow, I'm glad you brought that one up in particular because anybody from Stack Overflow here? Okay. I hate Stack Overflow because you have to dig through a bunch of people saying this question has already been asked. And then low-key making you feel bad for asking a question that they know the answer to. I think that AI is actually a benefit because the AI doesn't judge me where other people do. I mean, maybe, but it doesn't tell me about it. I've never been called a genius so many times as when I fight with AI. But I see your point. Like, we can't, raised earth in terms of like how we've trained an AI model. Like, that training has to persist and grow. And it's going to decay. We already know this. The AI ML people have been promising me an adorable robot sidekick that won't kill me for years. So that's an interesting point, but I don't think the solution is preserve Stack Overflow. I would like to see what we can all do that will innovate, that will make whatever the answer is. What do you think, John? Nothing?
I thought that I sympathize with people who are currently looking for jobs. I think this is a particularly frustrating time to be doing that. Although I can point to our final slide at the top. Bloomberg is actually hiring. So please have her reach out. This is very much my opinion. But I feel like as an industry, we go in boom bust cycles in terms of hiring and companies laying people off. And I feel like the latest round of people being laid off is partially using AI as an excuse rather than AI as the actual reason. And I think there have been quite a few cases where where companies go through and lay off a large number of people and then have to hire a whole bunch of contractors back when they realize that the AI does not actually provide the solution. So maybe the answer is that she should just start being a contractor for a little while, but I don't actually know the real answer, but I'm very sympathetic to it.
Like all of those COBOL programmers, remember them? And they were laughing all the way to the bank when Y2K happened. And if you're like, Y2K wasn't a thing, it was because of those people, right?
Yeah, thank you. And I wanted to say that Stack Overflow is like an example. So we can replace it with just articles. So I can read articles and distinguish there. So this one were written by AI. So it like when you see some image, you can distinguish which one were generated by AI. It's different, right? So that's why when you see some material, you also can distinguish it. So instead of Stack Overflow, there will be more poor quality of the articles or whatever. I mean, whatever data which will be using for the progress.
Good point. You just happen to pick the one I hate the most. So, yeah.
It's not really a question, but if you really hate Stack Overflow and for very valid reasons, I know a trick to make it work for you.
Sure.
So you need 2 accounts. You ask your question with one account, and then you give an obviously wrong answer with the other. And people will jump on that to point out all the ways you are wrong. And in the meanwhile, you get your answer.
And probably learn a whole bunch too. Okay, thank you, everybody.
Thank you.